Hi there, I'm Steve from Time Cost Curves. This is lesson 1 about project planning and how it is really time cost problem solving. This is something that this is all about the original critical path method for project planning, which was developed back in, I guess, the 1960s. And it was a fully developed and quite revolutionary way to plan projects. But in fact, it's kind of slipped off the radar, you might say, as the decades have worn on. I've read and learnt. First, I heard about the time cost problem back at university, so I've known about it for decades. And what I've now done in recent years is developed some software to solve this time cost problem. Yeah, as I said, I've been reading and learning all about how and why the critical path method developed and what its real purpose is, which is solving time cost problems. And how this purpose has been lost, in my opinion, is because the software that we've all come to use does not feature this purpose in terms of how people use CPM to plan projects. I would go so far as to say that what you're probably using CPM for is at a kindergarten level, whereas becoming a time cost problem solver, it's more about high school. It's at the high school level in terms of the concepts and the maths that you need to use to go back to the original purpose for using CPM in the first place. Being 2025, artificial intelligence may be the hype, but it's not going to help you in terms of solving time cost problems. Whatever it has been reading, the AI, is not, it seems to have skipped over these texts, which are in existence. Academia, academic literature is full of papers describing the time cost problem and how to solve it. A lot of it is very detailed maths, but you can reduce it back to high school level and still achieve the essential results. And that's what I want to present to you with this lesson. So I want to show you the critical path method is very powerful and what its real purpose is, which is solving time cost problems. So I'll go through the concepts, the certain steps, and what you want to achieve when you're planning projects. Essentially, the end result is down here in this graph, and it's a time cost curve, and it is all the rational project plans that you should aim for, and you can select to become your baseline. So I'm being a bit pedantic about the words and the concepts that I'm presenting here because it's essential that you respect the definitions, and it's the only way to stay on track as you work through some somewhat complicated, but as I said, high school level series of steps to solve the time cost problem. I would point out that every single project plan or every single project is in fact a time cost problem, and you as a planner should be aiming to solve this time cost problem. One way to do it is using critical path method in the proper way. Okay, so in this lesson, I am using one example, and all the graphs and the concepts, they relate back to the same example, so we'll go through that as we get to it. Let's start with some very simple definitions. What is a project? At the broadest level, you're setting out to achieve an objective or perhaps multiple objectives. And the reason it's a project is because it has a start and it needs to have an end. And then you perhaps go on to another project. So it's not ongoing. So you want to plan your project in the best possible way. And what that means is that you want to evaluate all the alternative means how you're going to achieve these objectives. Related to that, you need to use up resources in a in achieving these objectives. And they boil down to time and cost. Cost in the broader sense, not just money, but in terms of project planning, you're interested in the time-related costs. So they can be translated into monetary values, but it's more about the energy, the personnel, the effort that you're expending in achieving the objectives. And it just so happens that it's convenient and understandable to represent that in terms of money. But the definition of cost is not just money. Okay, so the time cost problem. As I said, you're only interested in the costs that are proportional to time. When you break down your project, which is an essential step, into certain activities and arrange them, each of these activities don't just have durations, they also have costs. And taking one step back, you need to always keep in mind that it's how you are achieving the completion of an activity, how you're carrying it out, is the essential determinant for how long it should take and how much it should cost. So for each activity in the network, it has a direct cost and a direct duration. If the direct, let's just say what if. What if the duration that you allowed for an activity was restricted? What might happen to the cost? It will go up. So the first point is that the direct cost goes up if the duration that you allow goes down. This is more or less a natural consequence and interplay between duration and cost at the activity level. At the project level, you have indirect costs that are proportional to time. And if your project is shorter, the costs that you assign at the project level will tend to go down. You can just use perhaps a thought experiment and just to prove that these concepts are essential and more or less you can't fight, you can't argue against them. So let's just say that costs were irrelevant to your project. Then what would you do? You would aim to finish every single activity in the shortest amount of time because you're just saying, forget the costs, let's just get it done as soon as possible. Okay? In the real world, that is not the case, except in perhaps very certain circumstances. And then flip it around. What if time was irrelevant? Well, then you would just do everything at the least cost. Okay? So those two things, I think everyone would agree, would be the sensible course of action if you said costs were irrelevant or time was irrelevant. Again, the real world doesn't work like that. So you need to plan for, allow for, and have a grasp on this interplay between direct costs and duration and indirect costs and duration. And they work in opposite ways. So the problem is you can't just shorten or reduce the cost to a project because there's this opposite interplay between durations. So that is the problem, and solving that using the critical path method is what we're aiming to do. So when you consider all these alternatives, you end up with a pretty soon astronomical number of combinations that you should be considering if you're doing your project planning according to this method. So I'll just point out here, you have 19 activities in this example project. All of these columns represent different means of achieving each objective, which have a duration and a cost associated. This is called utility data, which we'll define later. Okay, and you can multiply all these possible combinations and end up with 2,304 combinations. Remember, we're only considering a project plan with 19 activities. Okay, by solving the time cost problem, you end up with a time cost curve, which entails 37 rational plans. So we've gone from 2,304 to 37 that we logically should consider. Not all of them, 37. And of those 37, we can then choose a baseline of what we're aiming for. So this gives all the rational plans, essentially all of these points on the graph are the 37 rational plans that you, as a rational project planner, should aim for. So that is the problem. How to solve it using CPM starts with a network model. That can be displayed as a Gantt chart, but I would point out that you can hide mistakes quite easily in Gantt charts in terms of logic. And these days with the software, you can develop a Gantt chart which will not allow you to solve the time cost problem. Essentially, that's because all the different ways that you can link activities in the modern software is more misleading than helpful as you solve the time cost problem. So your network model must be valid. The best way to visualize a valid network model is actually with the activity on arrow chart, which was back in the day when CPM was being developed, was the natural way, probably because it lends itself to pen and paper. There were very few computers back then, but they got the logic right using activity on arrow charts, and that is your essential first step. Okay, you also need to cost load these networks. We go back to the problem. The cost depends on the duration, and so you need to have options per activity if you're willing and wanting to evaluate all the alternative means. Okay, so that means you have a normal way of carrying out each activity, but you want to, as a planner, consider alternative ways to carry out activities. So that is the meaning of loading the options into your network model. Okay, and then the end result of solving the time cost problem is plotting the time cost curve. And it has an essential shape, which is kind of a concave shape in between two limits, which is the normal way to carry out each activity. And that is defined as the least direct cost way to carry out each activity. It depends on the project, the resources you have available, where you are in terms of the rules and regulations, etc. And every industry, we all understand, has a normal way of doing things. But planning is about considering alternative ways which may be on the table, and by solving the time cost problem, you have a means of essentially evaluating all of these alternatives. Okay, that's at the right. Then at the left, you have the least time schedule. So we've gone from normal all the way to the least time schedule. And that is saying if time was more important than cost, you're willing to pay more, then there is a natural limit to your network model where you cannot compress, you cannot go any faster according to your definitions. And that is here at the least time schedule, and that has a certain cost. So in between those two limits, being a concave shape, you have an optimized for time schedule, and that is the least cost schedule. So that is, I guess, your what rationally, if you didn't consider any other factors, you would aim for. That is the project duration, which gives you the least cost that you need to outlay. Okay, compare that to the normal method, you're saving both time and cost. Why? Because of this interplay between direct cost going up if duration goes down versus indirect cost going down if duration goes down. So that's what all these calculations allow you to plot. All these numbers or labels attached to this graph. We have normal here. These numbers correspond to the activity IDs. So we've got from 2 to 19 with the summary as number 1. So you need to look at each activity and say, okay, we've saved 1 day here. What's the effect on cost, and how did we get there? Well, for the first step, to save 1 day, the cheapest way to achieve that was through activity 16, and that's because you have options at activity 16 in terms of how you're going to carry out that activity. So that is the essentials of time cost problem solving. Let's quickly look at perhaps what you do in your day-to-day project planning and how it differs from time cost problem solving. So I've sort of marked up the first chart and said, what if project planning isn't time cost problem solving? What's the difference between what I've just described in outline? In fact, worldwide, it's the normalized method where we're not considering the time cost problem, let alone trying to solve it. We're taking it more or less directed what the budget is and what the time allowed is, and we're perhaps, in my words, cobbling together a project plan in a feasible or infeasible way, trying to fit within these limits. Where do they come from? If you don't solve the time cost problem, you're just making some assumptions which may or may not be valid. Okay, and what we consider, if we do it this way, we're only considering one single schedule, the normal way. And all of the alternatives, which you should be considering, are being ignored. And that boils down to, because here we have the one normal method in the utility data, which is the key to solving time cost problems, utility data. And that's what your software does not give you. I almost guarantee that. This software which I've developed, as far as I know, is the only way to handle Gantt charts with utility data. So you're only considering one. And if that needs to change, which of course is going to change as you progress, you need to more or less go back and just rearrange your network model. Utility data should handle changes, allow you to speed up certain activities to get back on track. And then, of course, as a project planner, you're predominantly only considering durations, is my guess from my experience. And another department concerns itself with the cost, and they are not reconciled, I would say, in terms of costing each activity. The formats and the assumptions are quite often quite separate and not tied together, whereas in reality, as I've tried to spell out, they are in fact directly related. Okay, so what ends up happening? It's pretty normalized to be late and over budget because, of course, things change and you have no reference point for how to get back on track or how to achieve what you're planning to do in a rational way of minimizing any extra costs as you get back on track or try to finish early. Again, because you're only dealing with this one normal point, and when that changes, it's almost back to square one to redefine your plan. So you're ignoring all of those 10 to the power of etc. combinations, which you should be doing you should be evaluating as a planner. You're only looking at the normal one. And a slight digression is because the activities that perhaps you're listing have a built-in assumption if you are attaching a duration to those activities, which of course as a planner you're doing. But those assumptions of how you're carrying them out, I mean, in a practical sense, you're saying, well, we're doing it the normal way. But project planning is about evaluating alternative ways. So you are using CPM, but it's kind of at the kindergarten level, whereas you should be at the high school level, being a project time cost problem solver. So you're oversimplifying, but also in some ways you're overcomplicating um, in terms of the different ways you link projects together, the thousands of activities and pages where you tie all of these things together. Uh, and quite often, in the end result, the people carrying out the work perhaps ignore. That's quite common. Ignore the mega schedules that you're producing because you're only, again, getting to this one point, and it's based on so many assumptions which make it brittle and easy to uh, perhaps fall over. So your Gantt chart may or may not be valid, and as I've said before, it's easily concealed unless you view it as an activity on arrow chart. Cost loading schedules is seldom done in my experience. As I've said, options loading, never before, as near as I can tell, is there any Gantt chart critical path method software which handles utility data, except for what I have developed. Here, the most options you have per activity are 4, but my software allows you 20 alternatives. Okay, so that is sufficient, and it's certainly 20 more than other software. Okay, so you're plotting only baselines, whereas going back to this graph, you can see we had 37 potential baselines, which you then get to choose from. Okay, you're only working on the normal schedule. Overruns are normalized, I would say. And the bottom line, the only measurement even possible with this graph is just your experience or your subjective gut feel, perhaps. And again, I'll try to explain it. It's based on so many assumptions that easily fall over, and a more dynamic, comprehensive way of planning is to solve the time cost problem, where you end up with a time cost curve. Okay, so now I'll go on to the website, which perhaps shows how all of these things interplay, and I'll talk through each step. Okay, so this is timecostcurves.com, and under this tag, which is 3-span bridge, which is my example, which I'm using to explain all the concepts. So I'll start with what you need to get right first, which is the activity on arrow chart, and that's here down the bottom. You can see that all of these charts are moving as a GIF or a GIF, but they're not in sync, so don't expect that to make sense in terms of the synchronicity of all three. But here, the activity on arrow chart, okay, displays the critical path in terms of the heavy line, and you're only dealing with finish to start links. And as a time cost problem solver, that is the only link which you should concern yourself with. All the other links may allow your Gantt chart to display what you want it to display, but it is no help for you as you solve the time cost problem. Think only finish to start links. Okay, here we have the legend, which is the 19 activities, and the bold, again, is a critical path. And what we're doing, and you'll see the movement of it, is we are compressing this network. So if you had activities which aren't tied in properly, then compression of the network will become invalid. And that's why it's essential to tie them all together in a valid way so that you can compress the network and get correct results from doing that. Okay, the dotted activities are the dummy schedules. So that's logically saying, excuse me, that after a certain event happens, which is after a certain activity is completed, that completion of that event is tied into the start of subsequent events using these dummy logic ties. So that's why they change as the network is compressed. and it is the logic that ties it all together and again gives you valid results. So that is drawn from the Gantt chart. Here you can see the Gantt chart being compressed. You can see as each activity along the critical path, which of course changes, uh, you may have, in terms of saving one day on your project, you may need to compress more than one activity. And that's exemplified here. And the costs are also recalculated for each compression. So, yeah, the linkages are made here in the Gantt chart, but they're displayed here in the activity on arrow chart. And my software allows you to visualize both, which is a rare thing indeed. And it's essential to get the network model right. Hence, you should focus a lot on the activity on arrow chart. However, all the calculations are done in a more familiar format, which is the Gantt chart. Okay, so what's the end result? It's what you're aiming for, which is this time cost curve. And that is essentially a plot of every compression that we're making to the network and plotting the end result. I'm sure most of you are familiar with the S-curve concept. Think of each point on this time cost curve as the end point to a different S-curve. Why is it different? Because we're compressing certain activities, which is changing the overall, firstly, the direct cost, but also the indirect cost, and hence the overall time and cost of the project. Which activities are we compressing? They are displayed here on your time cost curve. So, in summary, yes, we're building Gantt charts like every good project planner does, I'm sure. But what we're doing then is compressing this Gantt chart in a valid way to say, what if we were equally concerned with the time and the cost? What are our options? It's not just a normal schedule which we're creating. We're creating, in this case, the 37 rational schedules that you could then go to your project team and say, we can choose one of these to be our baseline. Furthermore, as we progress through the project and certain unexpected events may happen and we need to perhaps get back on track, we have the utility data, which allows us to say, okay, well, unforeseen event, let's catch up a day or a week or a month. How are we going to do that? We need to refer back to the utility data, refer back to the time cost curve, and you will have a starting point to get back on track. Okay, so that's the essentials of lesson one. We'll go through, firstly, this one here is a screenshot of the utility data. So again, you can see the 19 activities. You have assigned resources to these activities. That's the leftmost columns. But your utility data allows you and the algorithm for this software to choose the least cost method to save another day, which is how the compressions work. So essentially, you have all the activities, you have a time and a cost, starts as normal, but what if we want to consider all our options? How are we going to do it? We're going to use utility data. We're going to go filter through all of these options we have, choose the least cost method to save another day, and that, of course, relates to the critical path, and hence the original reason why CPM has developed and is in all project planning software, but it's not implemented in this way. Essentially, the software is not helping you set up your project plan as a time cost problem, whereas every project is inherently a time cost problem. Therefore, we need software that helps us to solve this time cost problem, and that's where time cost curves, our company, comes in, and your end result should be a time cost curve. That is proof that you have wrestled with and solved the time cost problem. So this is something new, although it's all related to something that dates back to the 1960s. It is surprising to me, perhaps would be surprising to you, that it's taken this long for software to catch up. That's because I would say, um, again, using concepts but sticking strictly with definitions and combining all these concerns and issues and aims in project planning is best done actually in your brain, not relying on what software might be telling you. So that's perhaps a digression, that you need to query everything that a computer is telling you. And if I haven't mentioned it before, I'll say it again. AI is not going to help you because it is synthesizing or reading a lot of guff. They're my words. It's my word. A lot of guff which is irrelevant to the real problem of project planning, which is time cost problem solving. So thanks for your attention, and I look forward to presenting lesson 2. Bye.